In part 9, we turned a language model into an assistant. Fine-tuning, human feedback, alignment. As it follows instructions now, it answers questions. But if you've used one of these assistants recently, you know they do a lot more than that. They reason through math problems, they describe photos, they search the web and write working code. This is part 10, the last part of the series. We're going to look at what's happening right now at the frontier. Ask an early assistant to solve a word problem, and it would jump straight to an answer, often the wrong one. The fix turned out to be simple. Let the model think out loud. This is chain of thought reasoning. Instead of producing an answer in one pass, the model generates intermediate steps. First, I need to find x. X is 12, then y is x times 3, so y is 36. Each step becomes part of the context for the next token. The model can use its own output as a scratch pad. Reasoning models take this further. They're trained specifically to produce long thinking traces before answering. More thinking tokens, better answers. This is called test time compute. Instead of making the model bigger, you let it spend more time on each problem. A small model that thinks for 30 seconds can beat a large model that answers instantly. Training compute is fixed. You spend it once. Test time compute scales with the difficulty of the question. Hard problem? Think longer. The transformer we built in this series processes tokens. Text tokens. But there's nothing about the architecture that says the tokens have to be words. To give a model vision, you take an image and chop it into a grid of patches. 16 by 16 pixels each. A vision encoder, usually a vision transformer, turns each patch into an embedding vector. Now you have a sequence of image tokens. You feed those into the language model right alongside the text tokens. Same attention mechanism. Same transformer. Audio works the same way. Convert sound into a spectrogram, chop it into frames, encode each frame into a token. The model processes text, images, and audio all in one sequence. That's what multimodal means. Same architecture, different encoders on the input side. Language models are bad at arithmetic. They hallucinate facts. They can't look things up. Their knowledge stops at whatever was in the training data. But you can teach a model to ask for help. During fine-tuning, the model learns a special output format. Instead of just generating text, it can output a function call. Call calculator with input 9,876 times 1,234. The system intercepts that call, runs the actual calculation, and puts the result back into the context. The model continues from there with the correct answer. The same pattern works for any tool. Search the web, return the results. Run Python code, return the output. Query a database. Call an API. The model doesn't do any of this itself. It just learned when to ask and how to format the request. Now combine reasoning with tool use and add a loop. That's an agent. The model gets a task. It thinks about what to do first, it calls a tool, it reads the result. It decides what to do next. It keeps going until the task is done. This is a real shift. The assistant you used in part 9 answers one question at a time. An agent works on a problem across many steps. It can browse documentation, write code, run it, see the error, fix the code, and run it again. All without you doing anything between steps. The model itself didn't change. It's still just predicting the next token. But by putting it in a loop with tools and memory, you get behavior that looks like planning and problem solving. The scaffolding around the model matters as much as the model itself. Everything we've covered so far got better because models got bigger. There's a pattern to this. If you plot the amount of compute against the model's loss, you get a straight line on a log scale. Double the compute, the loss drops by a predictable amount. These are called scaling laws. But some capabilities don't improve gradually. They're absent in small models and then suddenly appear at a certain scale. In-context learning, where the model picks up a pattern from a few examples in the prompt, barely works in small models. Past a threshold, it clicks. Nobody programmed it, it emerged from scale. This is part of what makes the frontier hard to predict. You can extrapolate the loss curve, but you can't always predict which new abilities will unlock at the next scale. Let's zoom out. Here's the complete picture, the whole journey we've taken across this series. It starts with a single neuron, inputs times weights plus a bias through an activation function. Stack neurons into layers, you get a network. Train it with backpropagation. Specialize the architecture for images with convolutions. Handle sequences with recurrence, then replace recurrence with attention. Scale up the transformer with trillions of tokens. Fine-tune it with human feedback, and now put it in a loop with tools and let it reason. Every piece builds on the last. Nothing here came out of nowhere. The attention mechanism that powers every modern AI system is just a smarter way to do what RNN cells were trying to do. Scaling laws are just the training loop from part 3 running on more data and more hardware. The whole thing is layers on layers on layers. These systems are impressive. They're also limited in ways that matter. Models hallucinate. They state false things with total confidence because confidence and correctness are separate things in a language model. A fluent sentence isn't necessarily a true sentence. The model learned to produce text that looks right, not text that is right. They're also unreliable on tasks that need precise, consistent reasoning over many steps. They work 9 times out of 10, then fail on the 10th in a way that makes no sense. And there's a deeper question. Is a system that predicts the next token actually understanding anything? Or is it matching patterns so well that it looks like understanding? Nobody has a clean answer to that yet. The question of whether scaling alone can fix these problems is genuinely open. Maybe a model 10 times bigger solves hallucination. Maybe it doesn't. Maybe we need fundamentally new ideas. That's what makes this a frontier and not a finished product. That's the frontier. Reasoning with chain of thought, vision and audio through the same transformer, tool use and agents that work in loops, scaling laws that predict improvement and emergent abilities that surprise us, and real limitations that are still unsolved. This is the end of the series. 10 parts. We started with a single neuron multiplying inputs by weights. We ended with systems that reason, see, and act. Everything in between was one idea building on the next. No magic, just math, data, and compute, stacked up in clever ways. The neuron from part 1 is still in there. Billions of copies wired into layers, trained on more text than any person could read in a lifetime. If you made it here from part 1, you now understand how AI actually works. Not the marketing version, not the hype. The real thing, from neurons to the frontier. Thanks for watching.